Alrighty. Hey guys, what's going on? Memes here. Yes, we are back. Back in action. And we've done some further calculations and stuff. And we'll see. We'll see. Again, I'm not a quantum mechanic nor mathematician. I am a crazy person to be pretending to be a science explainer on this internet of stuff and things. So let's get into it. Don't I may or may not have had a calculation running in the background for about the past hour or two. Um, before hitting enter, I long story short, I came across a topic. I went into it, and now I'm attempting to have Mathematica do a figure 8 test for a potential, was it Hopfion? In play. Long story short, is I went through it. It seemed to chat wrote a whole bunch of code and it's evaluating it. Then I realized it. I had it take a paper from 1996. It basically found that there was a trefoil toroidal solution to the skyrmion. Skyrmion basically, oh God, what the heck is that? Theoretical vacuum-based solution for quote unquote particle or forminess in 3 dimensions. Um, Again, I'm not a mathematician, I'm sure but long story short is they found something for the trefoil back in 1996. It took 50 hours of computational time on a supercomputer. I chat wrote a whole bunch of code. It started evaluating, and then after like 40 minutes, I'm like, wait a second, wasn't this done on the supercomputer? I'm like, okay. Based upon our current parameterization, how long should this computation take? I'm like, it's basically on a modern MacBook. I know it's been 30 years since but I'm like, long story short, it's like, it might take half an hour, it might take like 2.5, 3 hours. So I'm like, I'm going to attempt to keep going. So things seem to be running. So let's open ourselves up. Open recent. This guy. All right. Let's share the class. All right. That dang cow. I know, it's terrifying. Okay. So don't mind me as I'm just randomly going to another side window to look up something that I may or may not have liked on Twitter. Okay, I renewed my license and now my little shortcut thingy actually worked. I can hit enter twice and it'll actually do the real input rather than on the other version where it's like, am I losing my mind? Why is this not working? I know it worked before. Okay, let's see. Where are we? Actually, will it work for this version? All right, let's so we're just gonna copy and paste this and just put this all in just a normal uh Mathematica notebook. Oh, hold on. If will it actually work if I just do this? Which version is this? Blah blah blah. Mathematica Home Edition. File. No. Let me just make a new one from this notebook. Okay. I'm literally just gonna copy and paste this all. Alright, put this in the new notebook. There we go. Oh god. Interconnectability or interoperability. Alright. No, 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 no. Oh god, I almost quit out everything. Oh, that would have been terrible. Alright, what do I need to do? Okay, I need to stop sharing this, so it'll actually let me click out of it. Alright. Click out of that. Alright, don't save that. And embiggen this text. And let's share this one. All right. All right. So let's save this. Okay. All right. All right. No, I'm not crazy. I'm not. Okay, I am crazy, but hopefully the right type. All right. So save as. Uh, Spherical God cow and the quest 4 more curvature. 4. Save to cloud. Because, well, one can't be too careful, right? I swear we will get to a point this time, and I'm not gonna let my own nature at being technically inept and trying to fight with an LLM to do something when I could just do at least the basic thing. Okay. What am I looking for? Oh god. I am so terribly disorganized. And I have to cross through Tritter for a particular notation style. God. Oh, geez. So much stuff that I've forgotten. I think, as some folks say, it's like, well, I've forgotten more than I've ever known. I don't know. You gotta make room where you forget you talk about. There we go. All right. Okay. So hold form. All right. Okay. All right. So we did that. So let me attempt this. Hold form. Let's actually just take some of this. That seemed to lag a little bit. Okay. Hopefully. Oh, wait, did the computation finish? Nope, still running. So let me just attempt some of my basic stuff and things. All right. Hold form. Okay. Okay, so it's at least running. Wow. I must be using so many resources on another calculation. I feel like it really shouldn't take this long. We'll give it a second. Okay, so well, I'm using far too many resources and that's running. Let's switch over to another window so I can actually not get to a point. Yes. Happy Friday, Tony. Good to see you again. I saw you in the Wolfram chat earlier, my friend. Absolutely. Oh God, Sebastian, I don't think you could call it that. I don't think you. Yes, I type a few magic words. I've become convinced I can't just, pardon my French, but half-ass it. I actually need to learn what I'm talking about there. Just because it makes things so much easier rather than it's like, okay, it's doing this. If it gives me the generalized framework and I can just go in and be like, okay, let me adjust this. Then again, I mean, how's that different than just an old macro or something like that? It's like, all right, I have to, heck, to be fair, I think the first code I ever wrote was a stop casting script for World of Warcraft. Why? Well, if you're playing World of Warcraft and you get about 100 to 150 milliseconds of lag, if you're a caster, the way it used to work is you needed to complete your cast before you could set in a new cast. So basically, in order to maximize my DPS, I would do a stop casting script right as I'm at like the last tenth of a second. Long story short is I could get out at least another 1 or 2 frost bolts over the course of a standard boss encounter. If you effed up, you could really only F up once, and you would still net out normal damage, and otherwise so it was a tactical thing. Yes. There's no DPS monsters. Something like that. Exactly. It's all right, cool. Hey, no, I look forward. Yeah, we're gonna be doing the monastery meeting at like 3 o'clock Eastern Standard Time tomorrow, 1 p.m. Central. Oh no, 1 p.m. Mountain Time, 1 p.m. Mountain, Utah, Colorado time. All right. Okay, I think. Let me just try just the standard. Higgs boson. Well, I think I gotta quit the kernel. Wow. Yeah, this, okay, hold on. So we're gonna do this. Unfortunately, I'm gonna X out of this just because this is annoying. I can always run something overnight. Alright, so just exit that. Okay. Don't save, and exit this one. Alright. Okay, yes. Don't save. Alright. Alright. Quit the program fully. We've quit out. We've quit out. Okay. Now let's turn it back on. Alright, let's go to our notebook number 4. Let's share again. Share the screen. We got the screen. Alright. So let's hold form. Let's see if this works. There we go. Okay, it did the thing. Alright. Okay, it was tied up with other tasks. Okay. Wow, that actually it's very simple. It's just putting it in. Okay, that's something I didn't know how to do, and then I learned from another Wolfram user on Twitter. Yes. Listen, Tony, I confuse myself all the time, okay? But I'm in enough trouble. That's why I'm trying to use all these... All I know is I watched that video from Professor Kipping. I did a quick live stream and now giving just my thoughts and opinions on it. I cut out a little clip. All I know is that was about a week or two ago where he'd attended that IHS meeting and a lot of the folks were like, yeah, we're using like whatever you want to call it, AI, different agents and models and stuff like that to help do research, as well as do other things for their lives. And he's like, it wasn't that he should necessarily be shocked. It was more like everyone was basically on the same page. And like, you didn't have it like, what? There was not one person there that was like, nope, it's all hogwash and everything. And then literally last night I watched Governor Maura Healey of Massachusetts literally say, yes, we're giving like all 40,000 executive branch employees access to like a chat GPT style agent to assist them in their work. And you sit there and you're like, oh my God. But then you think about it like, if you've ever done anything behind the scenes, let's face it, people do use Google. They use different search aggregation tools and stuff like this. And now with the more recent models, it's like their accuracy has gone up. So like, year or two ago, yeah, lots of hallucinations. Even Stephen Wolfram's like, is there such a thing as a blue wolf? And then it wove some elaborate story about, yes, this is a Tibetan blue wolf. And it was actually pretty convincing that Stephen Wolfram's like, all right, let me actually search. No, it was just imaginary. Just made it up. The multiple inquiries of like, is this actually a thing? So basically, when you set a prompt now, a lot of times they'll send like multiple prompts, kind of like writing itself prompts to be like, oh, what's the logical thing? And it's like giving citations. So just the magnitude increase. Ooh, man. Beautiful. Beautiful. Oh, dude, this is going to be great tomorrow. I'm going to try the short version without other computation, because if we can have like a literal physical toroidal model of different stuff, like whether it's a figure eight, whether it's a trefoil, this or that, like if we can also get used to doing these things, when presented with a different problem, we'll be better at tackling those problems. It's almost like education has a point, or at least in theory. I don't know. People have strong opinions about that. I think I got a lot of different educational stuff, so. All right. So let's not belabor our point. Welcome. Yes. You're slowly, exactly. Learning is good. Welcome, Charlie. Okay, so let's get to the dang point. Okay, so we got all these tables, so let's... Okay, so now the question is, will this actually compute? Okay, it's just doing the hold form. Yeah, So we don't need that. So let's do this. Let's give ourselves boy. Okay, so long story short is here's what we're doing. We're taking this whole quote-unquote spherical god cow thingy. What is this? So basically, as we see here, we're just taking the mass of the Higgs boson. Okay. So we got the mass of the Higgs there, according to Wolfram Alpha. It's around that range. We don't exactly know much, but we got about 3 significant digits, and then we got our error bars there. All right. So the vacuum energy density, I think I ended up just plugging that in. Just because Wolfram kept on doing this strange thing, so I'm like, all right, I just set the value to what, at least the Planck 2015 survey, and then the more recent stuff, the further we go, we get confused. I'm doing a lazy thing. There might be a future reason for this, we'll see. But we'll discuss in the future, hopefully. All right, so I got the speed of light. So long story short is we're taking the mass energy of the Higgs. So the mass of the Higgs. So basically, when we oscillate the Higgs field, according to what I learned from Professor Carroll, we produce a particle. So whether it's an electron, a proton, neutron, whatever, we believe that there's fields. Okay, I'm happy to accept that. Whether or not that's the ultimate thing, I don't know. We got a jiggle in the Higgs field. It's the one field that exists through everything. We get a Higgs boson about 125 giga-electron volts. Okay. So all I'm doing is multiplying this by c to get this out. That's what this is here. And we're turning into a spherical cow. Okay. Divide by 4/3 pi r cubed, where our radius, the thingy that we're cubing, is the Higgs associated Compton wavelength. Okay. And there's a little formula for it. It uses Planck's constant of proportionality to figure out the stuff and thing. And again, that's the general size of how we can talk about a particle having particle-iness, so to speak. Or, and again, I learned this from Professor Carroll. He says it, I'm like, let me just do something. And then I just was a little surprised that it seemed to come out to be a magnitude when you divide it by this, the universe's vacuum energy density. So that's about like, I don't know, like, was it like 5.3? 5.35 times 10 to the minus 10 joules per cubic meter. So the quote-unquote vacuum, it's not quite empty. It's quote-unquote no true vacuum, so to speak. At least we hope. This appears to be an energy density just in space itself. Okay. That seems like a weird thing, but that apparently it's a thing. Okay. AKA perhaps some consider it dark energy. Some folks may think that this is their mass energy term that you would put into Einstein's cosmological constant, or its kappa term, which is 8 pi divided by the Planck force. Okay. And it just happens to give a curvature scale of approximately 1 meter. Yeah, I mean, that was a surprising thing. I'm like, wait a second, this thing, okay. But again, that is our choice of units and this particular convention. You could say you should use the reduced Compton wavelength, which would, you just divide this by 2 pi. So again, to quote Professor Sean Carroll, a factor of 2 pi here or there. It's, hey, we're among friends. It's like, okay. The interesting thing, and this is the thing that we're going to do right now, is it gives you this. So long story short is this expression value here, this 1.01 or whatever, this is around the magnitude of the cosmological constant. It's about 1.1. Actually, is that math a little bit off? I think that math... Okay, it's using a 5 for there. It's actually 5.35. So I think I actually need to run this again. Oh, it's just putting that out there. Hold on. It should have been vacuum energy. Okay, so it was within there. Okay, so we'll need to fix that. All right, so no, edit undo. Oh God. All right, so note. Note. Update. God, I did a whole bunch of things I didn't like. I did things I didn't like. Do undo. Okay, so we're gonna do this again. We're gonna quit out one more time. Wow, I'm so bad at this. Adjust to the things. Da da da. Oh. So apparently, Jehovah says net worth is commenting. The curvature I'm searching for is located at the surface of pi of ice nucleation. So interestingly enough, just slightly above the freezing point of water, you go up a couple degrees. So basically at about, it's like 3.7, 3.8-ish, just a little under 4 degrees Celsius, water reaches its maximum density. It is just under, it's like 9.99, like 8 or something like that, grams per cubic centimeter. Okay. It's one of the reasons why it was originally used as the definition for the kilogram in the metric system. Water is a very amazing, seemingly magical thing. We're still learning all different things about it. That's at standard pressure. If you went up to about 1.5 bars, or 1.5 typical atmospheric pressures, there's a range where it becomes precisely 1 cubic centimeter, 1 gram per cubic centimeter. Some may say maybe that's a preferred reference density. Maybe we just got it right or something. Oh, I don't have the evidence to say that. That would make things very, very convenient. I don't know. Maybe that is the way. Well, yes, dimensionality matters. Yeah, in 2 dimensions, 3 dimensions. That's crazy. Is that 3-dimensional observers like us? 4 dimensions. What the heck is going on? How do we even try to think about that? Perhaps there is a way, but that's not what we're here to talk about today. Today, exactly. Who knows? Okay, let me try this one more time. Bring my thing back up and not break it. All right, open from recent. Okay. All right, share one more time. We've got this. We've got this. Big money, no whammies. All right, so let's actually just get to the point, because I at least know how to get to a point. So here's what we're gonna do. We're gonna do the same thing, except we're gonna put in another value for mass. What value are we gonna put in? We are going to put in the Planck mass. Okay, so here's what we're gonna do. Step by step, we're gonna do the exact same thing. We're gonna use, for this instance, we're gonna use our same convention, so we're comparing apples to apples. And again, maybe it's better expressed as an orange to orange. I just like this because it came out to be a roughly 1 meter for the Higgs field, so I thought that was cool. So what we're gonna do is, I'm gonna do this. I'm curious why it. Oh, did it just rewrite that another way? All right, it's running. It's sending it to Wolfram Alpha. Well, that didn't do what we wanted. Oh, Planck is a person. No, we want it to be a unit. Come on, you can do it. All right. Wait a second. Oh, that doesn't make. Wait, Planck? Planck is a joule second? I think they mean Planck's. We're talking about Planck's constant. Okay, angular momentum. Okay, but that's one. Planck's constant is. Yes, 1 Planck is angular momentum. Okay, so many Plancks. Okay, that's what it should be. Okay, that's kind of weird. All right. So We're just going to do this. There we go. Ah, there we go, my friends. So, okay, number one, we're doing the same thing. So we're taking the Planck's mass, multiplying by c squared. We're going to get the Planck energy. Okay, cool. Now we're doing the same 4/3 pi r cubed. Now, if you noticed, I multiplied the Planck length by 2 pi. Why? Because we were using a Compton wavelength, the previous thing. The wavelength is that. And if the Planck length is a minimum of length, long story short is you need to multiply it by 2 pi to get the minimum of wavelength, okay? So we want to compare apples to apples. So let's compare apples to apples. Long story short is, yes, this is much higher than our vacuum energy density of about 5 times 10 to the negative 10. Why? This is like 5 times 10 to the 110. Yeah. So there we go. We got a 120 order magnitude difference. Can we narrow this down? Is there some trick we can use? Okay. So here's what we're going to do here. Number one, we're going to pop that out. Okay. And then we're going to pop out some computable data. Okay. So we've got that right there. All right, as we can see, yep, that's our comparison. Okay. So we're going to go back. We're going to delete that. Okay. So we've got this thingy that we can compute here. Now, how are we even going to go about our computation here? Like, what are we going to do? Now, the last time, we multiplied by Einstein's constant, okay? Because that's basically our little curvature conversion thing. The 8 pi divided by the Planck force. So, where was it? That's the vacuum. Oh, did we even get to that? Oh my God, we didn't even get to that because I was such a noob. All right. So let's do this. So we just need to do the same thingy. Okay, give us that. So, wait a second, did I even? Okay, 120 orders of magnitude difference. Okay, well that's, okay. So what we're gonna do is, just do it right here. Let's copy that. Let's go down just above this, and let's do this. Well, actually, let's try the first one, just the first equals. Okay. Okay, so that's a normal calculation. Now, we need to multiply it by Einstein's constant. Oh. So what are we going to do? Einstein constant. Okay, it says the C2 convention. We want the C4. So it should give us assumptions. C4 constant. Okay, C4 convention now. Okay, there we go. So we're getting our output of approximately 1 reciprocal square meter, or 1 over meters squared, aka what one would expect the curvature to be of the Higgs field. Now, seeing as most of the general observable universe seems pretty flat, this does not necessarily seem to be the case. what might be going on. This is also one of the points where I can now say, like, the meter, at least of the magnitude of the meter, might actually have some significance, because essentially the curvature that would be induced at this scale. Okay. But again, if the Higgs is suffusing all things, what is actually going on? So long story short is we got about 1 meter-ish of curvature. Okay, 1 square meter. And again, I love that number because I can get a lot of toy models. I'm literally just injecting meters over like the Planck length, squaring it. So like I get that factor a lot. So when I saw this, I'm like, okay, I did not insert this factor. This just kind of popped out. So that they got me a wee bit giddy. And again, note, it is not precisely 1 meter. In order for it to be that, the Higgs would actually have to be a fair bit lower. And again, there have been measurements. Long story short, it has to be about 124.5 GeV at that point. If you want to be precisely 1 meter as we have it defined. Maybe we should base the meter on this if we got higher precision. But to be fair, the prevailing term is accuracy in the gravitational constant, so which we only got 5 digits to. So, all right. So we've got that. So basically, that's the curvature induced by the Higgs. Okay. So, yes. Output. Well, let me update that. Oh, does it have the little thingy here? So I'm gonna adjust the code or. No, we want. Oh, where did I put that? Oh, geez. Did I roll it up? Huh? I literally just, wait, no, it's here. Here. In here. No. There. Okay. More. Speed of light. So rather than confusing this, let's just do it. Let's just put in the dang actual equation, shall we? It's because I'd rather not argue over what the heck kappa version it needs to be. Okay. So we're just going to do 8 pi divide by Planck force. We'll protect the brackets over it. All right. Okay, now we can evaluate it. It's doing weird things. It's doing weird things. I don't like that. I'll just do this one. Oh, God. Constant array. Okay. Send the wolf from alpha. We'll update the thingy. We will actually get to the... What do you mean you don't know? Okay. I now see why people get annoyed at stuff. All right. Let's... Times Einstein constant. Okay. Now... Show all results. We want C4 convention. Speed of light raised to the 4th, because that's what we're working with. Okay. Got that. Beautiful. All right. So now, let's actually do a hold form of that, just because this is seemingly, okay, get that, all that. Oh. Oh. It's interactive. Oh, okay. So what are we doing with this? Subpod shift enter to request subpod. Okay. See, we're like, oh! Oh my god, it did the thing I wanted! Yay. I have no idea if this is computable data or not, but let's see, is it? Okay, so it's giving us the exact same thing. I mean, that's... Alright, so we at least got that thing. Okay. So what happens when we do this? This is... Okay. Show details. Okay. Oh, wait, will it actually do a table form? Oh. Okay. Shift enter. All right. Okay, table form. Okay, it's got that. Constant wavelength, blah, blah, blah. Not sure that's what we really wanted, but okay. Let's just output that subpod. So basically, we're just gonna get our state. Okay, I guess this is either a new thing or I've just been using the other version for so long. Okay, so our unit conversions, blah blah blah. All right, so put there. All right, so we at least have the data, and we should be able to get it in some form of computable form. I think it'll let you evaluate cells. Yeah. Okay, so let's evaluate. Okay, it's got the notational thingy, so I think that's good enough for right now. All right, let's see. Ooh. Antonius. Let's see. That's people, I think Charlie's commenting on some weird phase transition between classical physics and quantum. That's, see, the astounding thing is I did a little video on the chonkiest Schrodinger's cat yet. They throw in some like 170,000 atomic mass unit things in there. It's like, long story short, is like thousands of sodium atoms or something like that. So it's like, that seems pretty big. Still ridiculous, but they're still seeing like weird behavior. What might be going on there? I don't know. I think the keywords are usually something, something emergence or decoherence or something. So it's getting very interesting to see what might happen. Da, da, da. Yeah, that sounds about right. So basically, that's the limit of how you can talk about a particle. If I can remember from Sean Carroll, that Compton wavelength is about where you think the particle may or may not be, or you can talk about particle-y nature. Yes, and again, it's the Compton wavelength is literally Planck's constant, whatever the mass of a particle is times the speed of light. It'll give you a length, and then if you do the speed of light squared, it'll give you like a time or something like that. And again, not necessarily it's the k time or observed decay time, but at least some magnitude where Planck's constant is proportion. We'll do that on another thing to actually go in what's happening, because it took me for a while. It took Hans pointing out that I had a definitional loop there, and then I actually kind of figured out what the loop was actually doing. Yeah, the phase transition, and I've heard folks say this for the Higgs, because to my knowledge, and again, I'm not a quantum mechanic, the Higgs is a quote-unquote doublet. What does that mean? Oh, something about two. When you go into the formulation of like the Higgs mechanism, you'll see a box, there'll be a zero, and there'll be a bottom thing for like the actual Higgs axis. So we're almost kind of like setting one of them to zero. Why? Was its energy used up or whatnot? And again, I would talk to an actual particle physicist or physicist that has studied these things to see what the actual interpretation is. I'm just like, all right, well, one of these things we basically set to zero or we fix it. All right, this is our, what is it? It might be that you fix the mass, and that's technically the zero thing, and then everything else is the Higgs action. I don't know. I looked through it at one point, and I did some calculations, and God, there's a reason why a lot of physicists set h bar equal to c equal to 1. The notation gets very cluttery, but I'm happy I kind of went through it. All right. People are commenting on things that we've seen and everything. Okay, more cryptic messages from our friend Jehovah says. It's located at the magnetosphere of Earth. Every once in a while, I'm like, maybe that's true. Then again, there's some very interesting things, as Sebastian has said, about where we choose to put our boxes, whether they happen to be squarical or spherical. All right. That said, let's attempt to put the universe in a box. God, that's such a blasphemous thing to say. Okay, so we've got all this stuff for an reciprocal meter. All right, so let's move this guy here. You go there. All right. Let's delete all this jazz here. Is this the actual thing? Does it have the right? All right, C4 constant. So I do shift enter. All right. So we've got that. All right, so that's the curvature that we're working with there. All right. Like that. Oh. Okay, so C4 convention. So let's tuck this guy up over there. All right, so that's our output for that. So we've got that. Okay, let's do this computation. Quick file, save. Because if you're actually going to get to a point, you might as well not have to go through the horror of doing it again. Although once you know how to do it the first time, it becomes far easier. All right. Hold on. We want it to be a little bit more interactive than that, right? Let's just do equals. I'm going to run a quick interpretation. Oh, is it going to do, is it going to do the, no, interpret. All right. Okay. So let's output that. Let's output that. Okay, so we got a little computable thingy here. Oh, okay. Wow, this is actually kind of nice. And for reference, yes, that's about 120 magnitude. Long story short is, this is just the Planck pressure if you took out that 4/3 pi and that 2 pi in there. So basically you're just putting the Planck energy in the Planck volume. You get the Planck pressure. Under pressure. Okay. So, and you can do that with the other thing. It's just, you don't have the gotcha thing of like, oh my God, it's... So again, maybe this is just a state of convention or something. Because we're going to try to see if we can parse this into a way that makes sense. Okay, so let's see. Did we even output the other things? Okay, so it got that one. The ratio of the energy. Okay. Why is it overwriting each one? Is that just because I had the wrong thing? Or is it only supposed to give out one per? Am I just hiding it there somewhere? Help! Okay. Okay. Right. Hmm. Okay. That's what we want. So, okay, I'm just gonna hide this. I'm gonna move this over here. Oh, don't get rid of my data, bro. All right. It's a request. Okay. Okay. All right. That's okay. Apparently, I need to hide my results. I need to move them down. It just auto writes it. Okay. All right. I think I understand. Maybe I'm going to assume maybe this is a bug, or maybe they didn't want you to. I don't know. Maybe it's a new feature. Maybe I got to submit all these bug reports. Apparently, one of the biggest bug submitters eventually just went to work with them, and it's like, ah, yeah, I should work. I don't know. All right. So we can output all our wonderful stuff over here. Again, move it down. Okay, that's the thingy that we're doing there. All right, lovely, lovely. Get our actual expression here, output. All right, so we'll have all the stuff that we can actually play with. Three, all right. Is that, that's because, hold on. I just, I think I know why this is how, it's just, we have, 1 over 4/3 pi, and then we got a 2 pi in there. Boom. I'm sorry, I'm just on Wolfram Alpha right now, and then 8 pi in the numerator. So 8 pi equals oh, because I got that 2 pi squared, or cubed, sorry. Okay, 3 over 4 pi cubed. Does that even make sense? What does it output? I think to just make an error. Quinine? I. That's weird. All right. All right. Well, that's not what we're looking for. Okay. So we're not gonna worry about this. All right. So we got our general expression there. Okay. So we at least have the input interpretation. Right? Okay. Okay. That's fine. So it wants us to evaluate. But we already have our answers and stuff. Okay. That's fine. So We no longer need this. Ah. Oh God, no. We lagging. So, okay, because now we can change this. All right. So now, okay, now we need our kappa constant. All right, so file, save. I know. We'll be wrapping up soon. Don't worry. We'll get to the point. For those that have stuck around this long or are joining us at this point in whatever reality we're at, yes, we will get to a point. Okay, so that's what we're gonna do. I'm gonna copy that. We should need. Okay. Okay, we got all that jazz right there. Enter. Now let's play with cap. All right, so Einstein constant. All right, so we're literally same framework that we did for the mass of the Higgs field, assuming a 4/3 pi r cubed using the Compton wavelength. All right, so that output approximately a curvature of about 1 square meter. Basically 1 over meter squared. Cool. I mean, that's just a cool thing where it's like, oh, look, it's coming out with a magnitude of about 1 for these things. So, yeah, maybe it's probably nothing, but maybe we could tell something. Now, let's compare it to something else using the same convention. Planck mass. Okay. Now we're going to need to go through and let's check our interpretation assumptions because on Wolfram Alpha defaults the C-squared convention. So I'll give you a time thing. Okay, so that's, yeah, that looks about 1 over the Planck time squared. Okay, so that's giving us a time convention. But because we're using the Planck mass. So there's these conversion factors. That's why they're technically ones within the system. Or limits. Or boundaries. Boundaries is probably the best term. All right, so let's go to our C4 convention. Why? Because we seem to live in 4 dimensions of space-time. Okay. As we can see, per meter squared. Wow. That's a lot of curvature. Per meter squared, reciprocal square meters. Maybe this is the string theory thing where it's like, all right, well, this one, that amount of curvature, you're going to have all these smaller dimensions curled up. All right. I'm not that smart. I'm not a string theorist. So I'm like, what if I took this as the curvature induced by assuming the Planck mass? For those astute individuals, this is very close. Basically, the factor of that 4/3 pi and then the 2 pi within the Planck length. Yeah, that difference is basically it would be the Planck length squared or 1 over the Planck length squared. So, but I'm like, all right. Echelon mentioned something about information on the boundary. I'm like, well, I've been working with looking at some of Bill's stuff, become more familiar with the Bekenstein-Hawking relationship. So I'm like, all right. Again, assuming a Schwarzschild black hole, even though we've never observed one of those, because everyone that we believe we've seen appears to be rotating, doing all its stuff and things. So it's like, what if I assume this was an area? A straight universe, again, small u universe, because who knows what's out there. If there happens to be a limit, if we're going to claim, at least in this context, that there is a limit, I don't know, the RB Dragons. It's, LDG, what's going on, my dude? Good to see you. We need to catch back up. There's very interesting things and times are changing, so. Heck of a ride. One heck of a ride. All right, so let's get to the point. Okay, how we want to do this. Shift, evaluate. 3 over 32 pi. I don't like. I just don't like that version. It does. Let's just do this. Output. Okay. There we've got an output. Now let's see if it's just going to override all these things. So you got a little computable thing there. Output. Okay, so it seems to just be overriding it. All right. So let's do this. Unless, no, it's not all wrapped up there, is it? No, no. Okay, so I'm gonna do the hacky thing. I'm just gonna, well, input it. I'll input it manually. Okay, so we got that now. All right, so now I can input that. Okay. So, just gonna put a plain text cell in the way. There we go. We've got our buffer. God, so hacky. Such a hack. It works. It works. Okay. Let's just play with our cells. Put them over there. Again, we're saving as we're slowly making progress, so I don't want to completely lose my mind later. Okay. So that's really all we need. All right, so the claim is maybe this would be induced curvature from utilizing the Planck scale. Everything doesn't seem to be all wrapped up, so maybe there's more going on. So I'm like, all right, well, this is the number I really haven't played with in a particular form. So what's the Bekenstein-Hawking radiation? Hold on, we should be able to do this. Hawking radiation formula. Formula. Okay. So the mass, eh? Huh. Is this different than, let's look into our interpolation assumptions. Oh, we're trying to okay, it was trying to calculate for power. Why does this look different? Oh, I solved it for information? Hold on. Wikipedia, did you lie to me? Bekenstein, Hawking. Hold on, let's go over here. Share this window. Share this guy. I just need somebody to verify that maybe I'm not just seeing things. I mean, maybe that was the, yes, you visit the site often. Okay, so this is basically the entropy for a black hole. All right. So, let's have an input there. I need to play around with these things. So I don't know. When I hear about folks, this is well studied, it's like, I usually just ignore it. It's a terrible thing to do. All right, so we got Boltzmann's constant area 4 Planck length squared. All right. So the claim is, according to the Bekenstein-Hawking thing, we're going to use something that I've done some practice with, looking over amplituhedron or Bill's work. So basically, Boltzmann's constant area. Our last thing at output in inverse meters, but I'm just going to do the hacky thing and say, well, what if that was total area of our realm? Because if you assume that, and again, I'm just doing some calculations. I'm seeing if anything interesting pops out. Okay, so we need for that. So what we're going to do is we're going to go back and stop sharing that. We'll go back to our notebook. Tony, if you have another calculation for me, by all means, feel free to share. Yes, this is... I'm not even gonna go with Landau. I'm just gonna go with this to see if I can. And again, this probably almost certainly wrong. Can almost guarantee that this is wrong, but it was a very interesting perspective. So let's okay, so we got that stuff there. Okay, so we don't need this anymore. So let's make sure we're not deleting here. Okay, so I got the stuff that we wanted. Okay, that's the standard stuff for the Planck mass. This would be the energy. Basically, if you take the Planck pressure under pressure and divide it by 4/3 pi, and you use Planck length times 2 pi to get a wavelength. Okay, so we're trying to compare apples to apples here. We may end up having to switch to oranges, full disclosure, but did I not delete? Oh god, how many times did I do this? Okay, there we go. Okay, I got this term. That's a really big number. Let me just see for. Okay, so we're only gonna get that many digits. Will it give us more? Is there any easy? It's the pressure. Okay. Okay. Oh, wait, we didn't have the Higgs mass. Shouldn't we have more? Well, that's all it's really giving me. Okay, well, beggars can't be choosers. I think the next digit's probably either 0 or something like that. It's okay. Again, we're looking at of magnitude things. So let's take this number, and then we'll do. So we got Boltz and Boltzmann's constant. Times this by 9.26. Oh god, 9.26 times 10 raised to the 67 meters squared. Okay, so that's a freaking ginormous number. That's a lot larger than 1 that we got from that conjectured Higgs field thing for the spherical god cow that I. God, it's such a silly thing. All right, so meters squared. All right, so now we need to divide that by 4 Planck length squared. Okay. So now the claim is that we are dividing this up into Planck areas. Hawking corrected Bekenstein's formula to get the precise relationship to 4, according to our knowledge. And again, I have no idea if black holes actually irradiate or giving off. See, the thing that confuses me is it's like, all right, like you get a particle and antiparticle appear on the horizon, and then it's like, well, the antiparticle goes in and it shrinks, and I'm just like, I'm probably totally messing this up, but I'm like, but how do we know it's an antiparticle? Couldn't it just be the normal particle? And in that respect, wouldn't it just gain mass in that instance? And if you assume just a standard distribution, it would just kind of net out. And again, this is a hypothetical thing. The way you get at this, in my opinion, is if we actually have detected Unruh radiation and we can actually like validate that, like reproduce it, because basically they're both forms of acceleration. If the gravitational effect is just assuming there's something really massive that's having this effect, the Unruh radiation is as long as you're constantly accelerating, weird things do seem to happen. All right, so let me just go through this computation. Boom. Okay. All right. So what it's giving us a ginormous number in the units Boltzmann's constant. That's basically the information constant. Thermodynamics. All right, so file save. All right, so let's see. Okay, so that's just what it's going to give us. Convert display unit as. Let's see if we do. That's not really as useful as what we really want. So edit, undo. All right. So let's do, just send out the full results. Where are we? So go to Wolfram Alpha and give us all the information that I'm God, why? Why? I'll show all results. Oh, why didn't I just do that from the start? Oh, wow, yeah. I don't need any of that information, thank you. Oh, God, I deleted it. Where? Where did I go? Oh, no. Oh, wait, it's right here. I just wrap you up somewhere. What? Why are you being difficult? That's why we can't have nice things. All right, we'll do it again. All right, so we're looking for Boltzmann's constant 9.26 times 10 raised to the 67 meters squared divided by 4 Planck lengths squared. All right, boom. All right. The full thing. Okay, so that I just need to have it show all results because that's what we wanted. Okay. And where did we not want it? We didn't need this guy. All right. Okay, so this is bothering me. Why is it deleting that? Oh, I asked it for all answers. Oh. It showed me the answers I wanted and the ones that I didn't. Okay, so. Okay, will it disappear? Ah, it didn't disappear this time. Progress. Oh god, I'm the saddest individual. All right, so output please. Okay, we're gonna put an imaginary cell, so it's not just gonna delete everything and annoy me more. A little computational thingy there. Okay. Got that. Move you there. Boom. All right, we're slowly learning, folks. We are slowly learning. All right. So let's put that. Okay. Yeah, the Boltzmann's constant. All right. So go there. Let's actually put you there. There we go. That's kind of neat. And we'll get our little computable friend over here. All right. So as I learn more, we'll have more stuff to play with. All right. So that's a ginormous amount of Boltzmann's constant. It's basically the Planck length to the fourth in Boltzmann's constants. Because if you do, what was it? Oh, hold on. Sorry. Planck length raised to the fourth is about 10 to like 139 or something, or 1 over Planck length to the fourth, sorry. A lot of times you'll see like a Lagrangian, it's, oh, we need 4 dimension, 1 over length, or just something, okay, yeah. So basically there's a couple of pi factors between the 10 to the 139 and the, what was it? 10 to the 136. At least when I played around Wolfram Alpha far too late at night, that's what ended up coming out. So All right, well, maybe this, I mean, to be fair, I mean, we had a factor of the Planck length squared in there, and now we're dividing by 4, another Planck length. It's going to give you a really big number. So, and again, there are assumptions built in here, so full disclosure on that. All right. So it gives you this number of joules per Kelvin. Well, if we're trying to figure out curvature, we need to figure out the mass energy that might be present. So let's do joules per Kelvin. Oh, hold on. So now the question is, what do you put in? This is such a ginormous number. Even if you put in the cosmic microwave background, maybe I can tell you a bunch. we're going to literally plug in another one, which is absolutely crazy. And again, caveat after caveat here. we're gonna at least look to get close to something that resembles reality. And how do we do this? Okay. 1, we save. 2. Hold on, I need to check my clip notes. You know, that meters, we have that. Okay, long story short is we're just going to multiply it by the Planck temperature. So we're going to take this whole expression and we're going to change it. Oh, God. Oh, where do we go? Okay, so we're going to put some more protective brackets on this dang thing. All right, and then times Planck temperature. Go. Okay, now it's giving us ginormous numbers. All right. This is a really big number. All right. So, long story short is when I did a calculation before, if I assumed that if we have a maximum in our realm, and the Planck length is a minimum, the inverse should be a maximum. But then again, that given our convention of meters, that also infers that the meter might be significant, which you could make different arguments for. And I feel right now the strongest argument I have, at least, is well, if the curvature induced about from the Higgs is about 1 meter-ish, maybe it's not a crazy thing to use or assume that it might actually be a scale that's interesting. So that's kind of how we can justify it. Long story short is, I needed like 10 to the 96 joules for a maximum thing to match the vacuum energy. My previous thing, I was off like 17 orders of magnitude. I couldn't get there. Now, I'm not saying that there probably is a much easier way to formulate this that eventually we'll look at in the future and be like, oh God, this is so obvious. But again, seeing as it seems to be an open question, I figured let's try my naive hand at it. Oh, I thank you, Tony. Hey, you gotta try something. We're trying to figure this out, and a lot of times I'll have discussions with you guys on Discord or something. It's like, I don't know, but even if the conversation might not even be just like the echelon, just mentioning those key phrases, it literally prompted me to go in and do this. So that's how a lot of this stuff happens. It's like I literally am prompted to folks and be like, oh, that's an interesting thing. Maybe I should look at this, or maybe I should look at it from this person's perspective. Oh no, Dave, don't feel free to. That's the thing. Don't let me interrupt anybody. You do you. That's beautiful thing about this, because listen, I'm an old dude. I remember if you missed a TV show like Babylon 5 or Star Trek, you had to wait for it to come back on. Or go to Blockbuster or rent it or buy the collection. It's basically available after. It's freaking magic, dude. And again, I understand this science and everything. When you pressurize the orange juice, the dark. Donnie, I'm not sure. My email should be listed there. You can either always just do the memes of destruction at gmail.com to send me something there, or at meme destruction on Twitter, or I'm not sure if We might be. I think the Wolfram Institute does have an open Discord. Uh, if you go to the YouTube page or one of their bios, you should be able to get in there. But yeah, no, I'm curious to see other stuff just because a lot of times it's like, heck, even if I disagree with it, I'm like, oh my god, there's some mechanic in here that makes it easier there. And again, who knows what's actually right? I ain't no god nor prophet. I'm just again dude on the internet. Uh I'm just gonna say be wary on some of these agential models. Because one of the things that I would also suggest is be like, all right, critique this. Show me where the problems are, or falsify this. This is something that Kurt Mungle brought up because I think a lot of at least I've been using chat a bit more. If I try to propose something out there, maybe it's just because I've kind of prompted it. I'm like, all right, let's be open to new ideas, but like, let's give additional credence to like what we know, so we don't go off the farm, so to speak. But these models have improved and seem to get a lot more accurate, especially with just standard mathematical formulations. Before it's like I do a Wolfram, I've done the calculation, so I'm like, all right, well this is wrong, this is wrong. I don't really have to correct it as much. It's like I'll do it. I'm like, okay, well it's got it right using the numbers it had, so I'm like, it's very weird, but okay. So right now we've got a ginormous number. So I think we do need the curvature index. Where's our curvature? Okay. We need to do one more thing before we get there. Okay. Because if we're going to assume that this, and again, this was an inverse meter, so you can say that's just a naive thing to do. And again, yes, it is very naive. But we're trying to see if there might be, as to quote Professor Sean Carroll, something deeply hidden. Okay. So we've got that. So got our number. It's pretty straightforward. All right. So let's see. Do we have anything in the way? First, I'll put that. Okay. Do our little hack of inserting a cell so we won't corrupt our results. All right. I'll put that. We do need to go back and do one last step there. All right. There. Take our computable stuff there. I'll put it there. Got you. All right. Almost there. Almost there. Okay, mass energy squared. Yeah. Kilogram, blah, blah, blah. Okay. So, long story short is it's outputting joules. So, a whole lot of joules, but joules. Or at least using this convention. Okay. So you can see that's very close to the... Huh. Interesting. Okay. Sorry. My mind is... So we got that many joules. Now we just need a potential curvature. So we actually need to get that from this. So here's what we're going to do. 1, save. Okay, 2. Meters squared. And the reason I'm doing this, show all our results. Okay, because it does give us a quantity. So we assume there was a radius of a sphere. And again, maybe I should just be doing hypersphere, but this is within about a magnitude or so of what we're looking at, so we're going to output this. All right. Okay. Output that. All right, so make sure we just delete the part that we don't want anymore. No, edit undo. I deleted too much. Okay, only this one. There we go. All right, save. Now we have a number where we can compute some curvature. Why are we doing this? Because I need this number to calculate how big potential universe could be. Okay. So we should do that here. So this is a radius. Alright, so we need, I'm just gonna type this in. So, and again, you could, whatever convention you want, 4 pi r cubed. So, 2.715 times 10 to the 33 meters. Okay. This is 7 orders of magnitude larger than the observable universe. 10 raised to the... Oh god, I've gone through my ultimate battle thing. It's going on to Majin Buu's theme now. We gotta finish up. 3 meters. Okay. Cubed. Alright. So the claim is, this is... And again, I personally, I think it might be larger than this, but this is pretty close to the inverse Planck volume. Ginormous. Like, hold on. Look at the interpretation here. It's going to be like 10 to the 20 something times the volume of the observable universe. Yeah, 7 times 10 to 20. This volume goes up a lot faster, my friends. But this gives us a realm. This gives us something we can play with. And the reason we need to play with this is... Okay, so can I delete? We got most of the stuff we needed from that one. Make sure I don't delete it. All right, we still got that stuff. Okay, so got our imaginary thingy there. I'll put the value. All right, I'll put the other thing. Hold on. Okay, and I'll put the other thing. So just organizing the pieces. And then, if I've learned anything from watching enough anime, we should be able to form Exodia, the Forbidden One. God, I'm such a dweeb. Alright, so we're putting that there. Alright, so we're going through our conversions. Alright, ginormous numbers, ginormous numbers. Alright. So as a reference, yeah, it's about that big. Alright. Now, we're almost there. We're almost ready so we can actually try to form Exodia. Ah, jeez. Okay. File. Save. I don't think I've... Did I actually even finish this computation? Well, maybe, maybe not. Okay. So we're going to take our number for the vacuum energy density. Oh, can I do it this time? Universe vacuum G density. Okay. It's only giving us 1 digit there. Let's we'll do a slightly... I'm just going to take the number that I have. All right, so for this computation, we're going to need this size here. So here's how we're going to do it. We're going to do 2.515 times 10. 10 raised to the 101 meters cubed. So the claim is that is the limit in this formulation for the size of our, again, small u universe. Again, if we're going to claim there's a limit, then hey, who knows? Zarby Dragons. All right, so we've got this number here. Now we're going to multiply it by the actual vacuum energy density, which is like 5.35 times 10 to the minus 10 joules per meter. Was it? Oh, that was the wrong one. Oh, God. Okay. That was close. Okay, this is the number that I had put in. Because it agrees to Planck 2015, and we'll get into more detail in the future, but let's just finish forming Voltron. Okay. Where were we? All right, so 5.35 times 10 raised to the negative 10 joules per meter cubed. All right. So this is an energy density. That's appears to be vacuum energy density, whatever you want to call it. All right, we're multiplying it by volume, so that should give us, if the universe was at this size, how much energy would that require? Okay, as we can see, it's about 10 to the 90 something joules would be required. That is a lot. Okay, so actually, maybe if I just do, let's do equal. Let's give me more options. Show all the. There we go. All right, so let's output that guy. So we got our computational number. We'll put our little buffer thingy in there. Boom, that. Okay, now let's put the actual computation that we did. All right, so that's the thing that we're doing. That's the number, and then in standard SI, yeah, that's a lot of tons of TNT. Okay. Move that there. Boom. All right. So I got a lot of joules there. Okay, there. Okay. Now, that's what we're going to do. And maybe, again, maybe this is just a dumb thing to do. We're going to take... How do we do it? Okay, total number. So we're going to take... Okay. So I'm going to take this number. I'm going to take that many joules. And then we had a total number. We got this number in joules. Okay, so here's what we're going to do. We're going to do this. Here you go. Let me just rewrite this because I'll get confused. 1.346 times 10 raised to the 92 joules. Ginormous. So I'm going to delete that. All right, now we need this number in joules. All right, so we're going to use that divide into that. So we're going to need 1.7335 times 10. I know, I'm so inefficient. Raised to the 46 joules. Okay. So we're going to divide this. Okay. So the reason we're doing this is a very big number. it's kind of close to 10 to the 50-ish there, where if we go back up to some earlier numbers. Okay, this needs slight modification, but wait a second. Oh, that's around the cosmological constant. It's AKA the spherical god cow. Oh, energy density. That's in GeV, that's in joules. All right. So we want to compare joules to joules, so let's go back up to our spherical god cow statement. God. What was it originally? It was... I have it here somewhere. All right, so the Higgs mass speed of light divided by 4/3 pi r cubed, where it's Compton wavelength. I know, such a messy notebook. So we've got that ratio there. So now what we're going to do is save. And now, I think we divided it into it. Okay, here's what we do. I'll take this number. And then we're going to divide it by this number. So the claim is this is the maximum, quote unquote, energy of universe. Insane thing to say. We're dividing by the vacuum energy that would be required at its maximum extent. I have no idea where it's maximum. Who knows? I don't know. Okay. So I guess it's a dimensionless number, but we need to divide it into a dimension full number. I did that wrong. Oh, wait, no. This is the dimension full number. Okay, now we divide it that way. Sorry. I get confused about what's supposed to go where. Okay, 289. All right, we'll end it there. 10. All right, so the 54. All right. Let's see what happens. Give us some more results. What do we got? Okay. Long story short, we get this number here. Now again, there are factors off, but what the heck is this number? Convert to SI. Let's go to Wolfram Alpha. Well, a computer did it just confuse itself. Confused itself. So long story short, let's just send this whole thing to Wolfram Alpha. Let's, oh, unit conversion. Let's just do this instead. What the heck is this actually? 3.8 times 10 raised to the minus 12 kilograms divided. Long story short, this is pressure. This is an energy density. Meters. Seconds squared. All right. Yes. Give us the full query. We're getting to the punchline. No! No! Wolfram Alpha, no! Okay, there we go. Okay. Long story short is we're off by about 2 orders of magnitude right there. But one could imagine if we adjusted our pies and everything. Okay, let me go back. One will save just because that's kind of a hot mess. And that also infers that maybe doing the whole spherical god cow thing, maybe it's telling us something. Maybe we should just do it divided by its reduced Compton wavelength. Because, all right. So let's stop sharing that. Let's go to the actual thingy that I did before. Where are we? Okay. So it's here somewhere. Did I hide it? Where did I hide you? Far too many tabs. Okay, that one. Here we go. All right. So the rub is when. That's why I'm saying it's maybe if we just use the different things to its full use. So long story short, this is kind of the same thing using some slightly larger numbers here. Some different factorizations. And again, it went up by a little. It gives you this number here, 8.5 times 10 to the minus 11. Same units. Long story short is that's within about a factor of 6 for the universe vacuum energy density. So again, I'm assuming, and the energy density, I'm assuming that that is constant. So if we were at a maximum scenario of enormous, like 10 to the 7, 10 to the 8 times large, like basically 1 million to 100 million times larger than the size of the observable universe. You could put in the vacuum energy density. If you assume the Higgs field would have something like that, induced curvature, or whatever you want to call it. Long story short is we can get out the vacuum energy density that we observe pretty close. And again, there's probably going to be some factors we need to change in here to see what might line up. And again, maybe just a whole lot of hogwash. It probably is hogwash. But at this point, where did we insert like 10 to the 122 magnitude difference? I'm just trying to explain, or at least find some path forward. We can at least try to grok, so to speak, what the heck is going on. Oh God, I went on for 137 minutes, or an hour and 37 minutes. Okay, I'm done. I'm sorry. All right. Rupert's teardrop, the size of the Rupert's teardrop is one of the most amazing things that's going on. Again, feel free to share. Again, some things people keep quiet for different reasons. I've had interesting things that have been told to me that I may or may not be allowed to share at this moment, and hopefully in the future. I really think we're going to get a lot of very interesting stuff going on. Oh, sorry, Jax, I see you there. Melon, USK, welcome. Welcome from the X side of things. All right, well, we get a little impressions on the Twitters. Yes, I know, I've been rambling on about all this stuff. All right. So, since it said at least 137, and we're going through, I'm done at this point. All right. Save notebook, file, save as. Notebook 5. So at least it's a ridiculous method, but I'm like, well, when I get it more formulated and I grok more with this notebook, we'll go a little further into it. Save the cloud, because well. When your computer occasionally, yeah. When it dies or whatnot, it can be very frustrating. All right, publish to cloud. All right, and if anybody wants this mangled mess of a notebook, I'll throw it in the chat. All right. Dun, 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 dun. Oh God. Well, at least if it lags now, then. All right, there we go. So we can exit out of Wolfram. All right, there we go. All right. Please, everybody, get back to your lives. God, me just rambling on about speculation after speculation. So that's about all we got for right now. So hey. Thank you all for watching, and for those that may tune in the temporal future, take care of yourselves, everybody. It's a wacky and wild world out there. Times are changing, but I'm hoping this change is going to give us the impetus to do something really amazing. So, here's hoping for the best. Take care, y'all. Peace out.